Let's take a look at lesson 11.3, the normal distribution. Wow, this lesson's pretty cool. So what we've done in the past is we've analyzed probability distributions for discrete random variables. Now we're going to find values that are normally distributed over curves. And this is pretty neat. What it's saying is in a normal distribution, things seem to happen pretty symmetrical. And we'll have all these terms you'll hear a lot. You've heard the normal distribution. We're going to see that a lot. So I'm about to show you a normal distribution in a moment, but it says this: the graph of a curve is bell-shaped and symmetric with respect to the mean. So if you open up normal distribution here, I'm just going to give you an easy one. The standard is 0, 1. I'll show you what the picture looks like. What it says is if the mean of some distribution is 0 with a standard deviation of 1, you'd have a graph that looks like this, where if you plotted all the different random events that happen, if you had a whole bunch of data, 100 people did something, the values that would occur would look like this, where the value 0 would occur about 40% of the time, and the value 1 would occur. You can add all these up. Now, the area under this curve is equal to 1, which means if you had an infinite number of the samples and the average value was a 0 with a standard deviation of 1, and you plotted them in, you'd have a graph that would look like this, where all the values would be plotted in within here, all the different options. Every time someone was a -1, it added a little bit. Every time someone was a 0, it got higher and higher. You would look up and it would have this graph, and underneath it, the area from the x-axis to this curve would equal 1. That's what it's saying here. The mean, median, and mode are equal and located at the center. This curve is continuous. The curve approaches but never touches the x-axis, so it never actually gets there. It just gets closer and closer. And the total area under the curve is 1, like I was saying. So here it is. And what we will learn is if this is the mean, that's the mean, this is one standard deviation. One standard deviation to the right will have 34% of the data. One standard deviation to the left will have another 34%. So between one standard deviation left and right, 68% of your data will occur. Between two standard deviations, you will have 95% of your data. That's the kind of definition or the empirical rule for a normal distribution. That's how they line it out. When we find our values, it's by definition, the normal distribution, 95% of the values will occur between two standard deviations. That's how we'll come up with our math. And then within 3 standard deviations each direction, we will have 99.7% of our data. So here is an example. It says the heights of 32 peaks in a mountain range are normally distributed with a mean of 10,200 feet and a standard deviation of 295 feet. Approximately how many peaks are more than 10,495 feet tall? So here's the idea. We have 32 peaks, that's how much the sample is, with a mean of 10,000, type that in over here, 10,200, and a standard deviation of 295. 295. And now I'm going to hit this zoom. And so here's our normally distributed data. You might notice that if the mean here is 10,200 feet and one standard deviation is 295 feet, that the value 1045, that is the mean plus one standard deviation. If you added these two together, and the mean plus one standard deviation would be 10,495 feet. So that's why on this graph, this is right here, the mean. That's the mean. This is one standard deviation. This point right there is the mean plus one standard deviation. The x values I'm talking about here. So it would be better if I labeled it here. Let me do it that way. We want to know how many events would occur out there. So how do I calculate this in the calculator? What we're going to do is, if you have this submitted in, what we can do is say we want all the values that are greater than 10,495. And so underneath in this min and maximum, if I put 10,495, you will find all the values that occur that are greater than that, which happen to be about 15.87 or I'm going to just say 15.9%. How many peaks are more than 10,495 feet tall? Approximately 15.9% of the peaks are taller than 10,495. And that's because it's one standard deviation over. So remember from this slide that one standard deviation is 34%. So you have 34% right there. And from the from the halfway point over in all of this area, you have 50%. So if you added that together, that is 50 plus 34, which would be 84. And if you subtracted from 100, it would leave you with 16%. And that's where we get this number. This is just more exact here. So about 15.9%, or you could even say 16%. I'd be okay with that. All right, let's try part B here. It says the heights of 32 peaks, the same situation. This time, what percent of peaks are between 9,610 feet and 10,790 feet? So again, let's think through the math here. They told us the mean, the average value is 10,200 feet. And we know that one standard deviation is 295 feet. So this looks like from the picture, it's 2 standard deviations. So let's just say we wanted the mean minus 2 standard deviations. That would equal 10,200 minus 2 times 295. Well, 295 times 2 is going to be 590. And so if you subtracted 590 from this amount right here, that's where we're going to get the 9,610 feet. Just the same, mean minus plus 2 theta, or not 2 theta, I'm sorry, 2 sigma, is 10,200 plus 2 times 295. So 10,200 plus 590 is going to equal 10,790 feet. So that's where these numbers are coming from. This is our mean. That would be the mean plus 1 standard deviation. This is the mean minus 1 standard deviation. This is 2 standard deviations. So if we think about it, we should have 34% of our data here. And if I go back to the chart, 13.5 and 13.5 here. Now we'll see how when the calculator does it, it'll do it exact. But this is 68, and then you add another 27, which is going to be approximately 95% of the data. Let's see here. We want to go this time from 9,610 feet to 10,790 feet. This is, the calculator says, a 95.4% of our data, 95.4 of our data there. Okay, your turn. So given this problem, we want to know how many cars. So there's something, let me see, what percent of peaks? So mine was saying percent of peaks. If you need to know how many peaks, you could take your total here, the percentage. You could say 95.4%. This will help you. Times the 32.954 times 32, which is approximately, this is between, this would say between 30 and 31 peaks have heights between those values. So that's how you would interpret this data. And on the previous one, when we got 15.9, we would say 15.9% times the 32. Let's see how many peaks this is. We take 15.9 times that by 32. Whoops. 0.159. So 15.9% times 32 is around 5. About 5 peaks greater than 10,490 feet tall. So that's how you assess your data. So you'll need to do the same on this problem.